All right, everyone, we are back and we are going to get into our first lecture on controls. So basically, introduction to feedback control, Laplace transforms, transfer functions, giving us a strong background in order to be successful and enjoy essentially this part of the course. So I think controls is one of the most beautiful topics in all of mechanical engineering. It encompasses and kind of puts everything together. So you need to have a strong background in statics, strong background in vibrations, dynamics. You have to have a strong background and kind of put everything together. And I think especially your statics and your dynamics and your vibrations backgrounds are really critical in order to kind of understand a lot of the concepts in this course. But control systems are really ubiquitous. They're in tons of different applications. And again, the whole idea is a control system is going to basically continually measure essentially the system's output, compare desired input, adjust essentially those internal inputs or forces to minimize essentially your error. And it's going to, again, feedback like a feedback loop. To understand these systems, it is going to be critical and we're going to mathematically model these systems. And most of the time, for a lot of the systems that we're going to work with, they're going to be described by ODEs. So again, having a good ODE, math, PDE background is also really, really critical to understanding essentially these things. So those mathematical models have to think about, elastic restoring forces, dampening, actuation, friction, lots of other things, and we're going to, basically characterize these systems. We're also going to look at these system dynamics because, again, an ODE is time varying, right? When you're looking at something that is a time varying function, maybe not position, but we're going to then express them basically in the time domain or more common in the Laplace domains, and we're going to essentially establish why we are going to do so. We need to have in this course a strong background in dynamics or a strong background in vibrations. We have to understand how we can look at a system, describe essentially those equations of motion, because then we're going to take those equations of motion, ODEs, we're going to perform essentially a Laplace transform. We're going to take essentially time space, convert it into an S domain space, which is simpler mathematically, and we can look and actually leverage that Laplace transform to do mathematical operations a little bit more simply. You can convert the S into a frequency space, but anyways, the key, we have to be able to basically draw those free body diagrams and those kinetic body diagrams. So for example, I kind of skipped it over. This needs to come out and we should know essentially the description of this system. So we have to, and we really need to understand how to describe this system. So for example, we see the system, we have a coordinate system set up. What's our FBD? So we already have, this is our positive, basically X direction defined here for us, here, depending on the motion, X. This is basically 1D system. So we're only looking at that positive X direction. Free body diagram, free the body from the surroundings. So our body is the mass. What are the forces acting on that? If my mass moves this direction, there's going to be basically a force here. That force is going to be described as my damping coefficient times basically the velocity, or as we're going to describe our X dot. There's also going to be a restoring force here, our spring force, K, basically Kx. There's also going to be some additional forcing function here, F of t. Additionally, our kinetic body diagram, our body is basically moving this direction with some acceleration, m x double dot. So what do? Apply essentially our equations of motion, so Newton's second law. So we're going to say, let's look at the forces first. So for in statics, remember, some of the forces set equal to 0, but now since we're dynamic, some of the forces equal to mass times acceleration, which is mx double prime. We can kind of go ahead and set that up. 1 second here. And our forces here will be encompassed by, again, pointing in the minus c x dot direction, minus k x, and then also plus f of t. So when we do that, we can rearrange that expression and we can get this. This is the most important dynamic system that this has to come out almost immediately. We are going to be working with this spring mass, basically a single mass spring damper system over and over and over and over and over in this class. This is a second order system, and it is going to teach. This example will show us so many different concepts of controls that really, I mean, we have to understand the system. We need to come into this class with the understanding of, is it an overdamped, an underdamped, is it critically damped? What are the frequencies that you can kind of expect in this system? Knowing how to kind of draw these out, it's really, really critical. So we have to know this one. This should come out, this should almost be memorized essentially at this point. But you can kind of apply this, and there's lots of different cool systems. So this kind of 2 degree of freedom vertical suspension model, it's kind of like a quarter model system for suspensions. So you can model essentially a car suspension here with this type of two mass system. So that first mass here, M1 is just going to be the basically representing the wheel and the axle. M2 is going to be the chassis and the vehicle. So you can kind of model it with this suspension system. This distance here is this x naught, which is basically this fixed vertical position of inertial ground. But you can kind of take the same concepts here and write out those equations of motion, right? So now there's two mass systems, so we're going to have to actually write out 2 equations of motion. So again, let's just do the same procedure. Let's look at mass 1 first. So my FBD of mass 1, I always do. Yeah, let me give me some space. And now our coordinate system here, we're going the positive x direction, so M1. So if it's moving here, I'm going to have basically some force here, like as this extends, is going to pull this back from our K2. Our K2 and our C, there's also going to be that force here that pushes in the same direction here for K1, right? So these are 2 negative forces. So, and we can kind of basically describe those, right? So we're going to go ahead and say for mass sub 1, this is just going to be, and again, we're going to describe 2 positions, x of 1 and then x of 2, and then x of naught, right? So we're going to have to count essentially for that kind of difference in the motion. And you can actually see that right here. So if we look at first, this K1 is just going to be, K1 times x1 minus x naught here. And that x1 minus x naught, it is just going to be kind of this descriptor, right? So it's the distance where we're compressing essentially that spring. So we're going to move in this x1 motion here, and then it's going to subtract from this initial distance as well. What about over here? So it's going to be, we're going to take this K2, and as you can see here, we're going to basically put into here, that's going to be K2, and then x2 as this moves down, minus x1. So, and then for here, for the C, x2 dot minus x1 dot. Again, this needs to be your background, and I'm being kind of nice right now, but we won't be going over this. This needs to be kind of covered in dynamics and to kind of write these out. Your kinetic body diagram, again, straightforward. M1, let's just say we're moving in this direction. So now we can go ahead and say M1, x1, double dot. So my acceleration, so basically equals the sum of the forces. So MA equals sum of the forces in that x direction. And so now we're just going to be, remember now, positive is moving down. So it's going to be minus K1, x1 minus x naught, plus, excuse me, it's going to be, actually, yeah, we're going to be fine. Minus K1, and then we're going to say, also, yeah, that's also mine. It's going to be minus here because we're going in the opposite direction unless we're being pushed here. Excuse me. Oh, excuse me for a moment. As that pulls down, I think we're being pushed here. I'm just flipping those directions. Little notation there. So plus K2, x2 minus x1. I forgot about this mass moving here. So this is going to kind of compress and push those there in my notation. Plus, it would have come out in the basically C times x single dot, x dot 2 minus x dot 1. And there you go. Fantastic. So you can do the same thing for mass 2. and you can kind of write those equations of motion. There's also lots of systems where you have rotational dynamics. So you can have kind of like this problem of kind of a torsional pendulum, right? So you can have this system where you have a torsional pendulum, and you can actually see it comes out very similar, mathematically identical, effectively, to our mass spring damper system. So second order system that behaves and actually explains a lot of kind of concepts as well. And you can kind of see some of the system behavior. So again, it's expected that you can kind of reach this almost immediately. Remember, for rotational dynamics, some of the torques equals are basically rotational inertia, which is analogous to your mass inertia, and then alpha is our angular acceleration. We can write that as theta double dot, and we can get that system. We can work with pendulums and inverted pendulums. So pendulums, you can kind of see, and you've probably done this before in your torque. When you write out and you look at essentially those rotational equations of motion, you'll notice that this is a nonlinear second order ODE, right? We need to work with, and we'll kind of see in just a bit, a linear ODE. So we'll make kind of this assumption, simplify the system that we're around 0, and then we can get basically harmonic oscillation. Inverted pendulum is really cool because even when we linearize it, you can see that the solution is going to be this exponential, and actually it's unbalanced. So it's kind of like you can't basically stabilize the system without some type of feedback. So it's like balancing a stick on my on my hand. So really, really cool. We'll get to that. Gears and gear trains, there's lots of equations that describe essentially this. You can apply this to heat transfer problems and all these good things. So we have to understand these systems, and then we're going to work with them, and then we're going to describe it within our controls context. So see you next time. Thanks. Bye.